partial derivative. Okay, what is the partial derivative if? You see what is that? This is the I component of the gradient. This is the I component of gradient. So this is actually gradient f component of I. Huh? Mm-hmm. And what is that? Gradient dot v component of I. Huh? Because it's I follow this convention. When you have a dot between two vectors, it will be sigma I b. Just I accept it. This is the postulate. You know, I make postulate and I use it that. This is a different approach actually. Huh?
What about the scalar f?
Yes. So what about the scalar f? So here the role of the f is phi is played by the f. Partial derivative of the I. Partial
We put it first in the brackets, but we didn't put it in the next term. The other term.
Here, you mean? Here?
No, the last term of the equation.
Here?
Yes.
Okay. So what's the problem?
Where is it?
Partial derivative I and VI. It looks like RIBI, huh? AIBI. So it looks like A dot B because it's A dot B actually. Ah yes, with sigma it means A dot B. Yes, that's true. That's true. I understand. I get your point, what you mean. If I understood correctly. So I need to continue these calculations. So let me to calculate here. Continue. So I will have gradient Fi Vi plus F sigma I, huh? Rho the I Vi. So what is that? As I told you, the total of this is just the gradient F component I, and this is the Vi. So it looks like gradient F dot V, yes, plus F gradient dot V. This is the. So this is the first identity. So the first identity is that if you want to find the gradient dot something, so it will comes like first take the gradient to the scalar function dot to the vector plus second put it is outside the function and just dot make the dot operator to the vector. So this is the. But you have a new object again. So this is a completely new object. Yes. Del dot v. Let me to explain what is the del dot v or gradient dot v, and after that I will complete that. Gradient dot v is called the divergence of v. Is a scalar, is a number. And according to the definition, this is just partial derivative of the component of the vector with respect to the coordinate. So that's all. So if you want to write like engineering, you need to think about that like this. I will try to explain you the meaning of this divergence, because you have a good feeling about the gradient now. Gradient appear because you want to consider the total change in the function, df. df was the total change of the function from one point to the other point. Huh? So what about the gradient? Gradient interpretation is more complicated because we needed to think about a vector, yes? And this vector changes from one point to the other point, yes? So it looks like there is a fluid, yeah? Some fluid are moving. So it looks like there is a fluid which have the velocity vector rho, for example, or any other things. And it seems that you are interested to know that when the fluid is passed from the very tiny size, because why I write dx dy is because of gradient. Gradient comes from the change with the small size. So it seems that gradient.v looks like a change in the vector when passed from the very small piece of the system, and then the size of the system is dx and dy and dz. So this is the divergence is related to the flux, the quantity, call it flux. The number of the lines, if you want to think very easily, the number of the fluid lines pass from the very small, tiny element. At the unit times, this is the meaning of divergence. So divergence V is the rate, rate, or it's called the flux, number of the lines passing through an infinitesimal element. Delta x, delta y, delta z. Actually, using the fluid dynamics, not fluid dynamics, using the basic concept of the flux, you needed to know that what's the flux. You can go to the chapter 25 of Holiday Resnick, the physics, fundamental physics. You can find the meaning of the flux there. Flux is just the number of the electric field line passed from the surface. Huh? That's all. And it's given by one integral over the surface of that. So starting from the basic principle, you can show that if you start from the flux definitions, this definition, V dot dr, dr is the area. It comes from the fundamental physics. Fundamental physics. Just start it from here and think about the flux passed from the small cube here. The detail is already written in the RFQ. If somebody wants, you can go and see them. Just start it from here and think about the small cubic with the size delta x, delta y, delta z. You will get very surprising results. You see that if the element is area very small, so I can forget about the integrals because this is a very tiny cubic. So roughly speaking, that will be just V dot dr if the surface is cubic considered very small. And just started to find the flux. There is some fact here. You know, the flux, when the fluxes come to here, so V is, for example, x, y, z, and when we want to leave, the V will change, yes? In the x direction, in this value, and in the y direction, just y plus delta y, and in the z, because this is a vector, in the z direction, z plus delta z. If you consider 6 surfaces, up, top, right, left, and bottom, and the back, and just write the change in the vector in this 6 cubic, you will find, you will find that it will come like that. The detail is given in the book, so I want just to introduce you the important things because we have not enough time to derive all the equations. But you can go through the RFQ, you see that the mean is important for me. Divergence V is the flux. The number of the vector line passed from the infinitesimal cubic with the size delta x, delta y, delta z, and that's all. And surprisingly, if you started from the area, you get something is given in the body. This is the body. And you know that this is a divergence V. That's why I introduced it. So divergence V has the meaning of the flux. So you can have an object which they are divergence free object. When you find a vector and if you calculated that and you get 0, we call it these vectors divergence free or source free. you know why, again, we use a physical word of the source? Because as I explained to you, the divergence means the flux. The easiest example of the flux is electric flux. So electric field should start from somewhere and go to the somewhere and pass from the surface. So how you can produce the electric field? You need the source. So when the flux is zero, it means that there is no any source there. Or if it was very far, so the source is very far away. So when the electric field lines pass to here, so finally the net change in the vector will be zero. The net change in the vector field. Sometimes I don't repeat my statement because I don't want to destroy the words. So many physical fields are divergence-less. One of the main important of them is the magnetic fields. No any magnetic field can be obtained in the nature which, if you calculated divergence of V, so divergence of V be not zero. Theoretically, you can have the divergence of V not zero, but in the application, we didn't find it. These equations have a very deep meaning, and this equation. No monopole source. You cannot have the source like that and produce from that some lines, vector fields like magnetic or electrics. Monopole, magnetic monopole. You cannot have that as a magnetic charge, magnetic source, and you produce the magnetic field from that, and you put at the surface here, and you calculated the flux, and you get at the. You definitely need to get the flux to zero, and this is because of that. That's the reason that we say that we don't have the object in the nature with the one magnetic pole only. We have an N and S already. We don't have the N. That's because of this equation. This equation guarantees that. If you can find a single monopole in the nature, so the divergence from these all the discussions, the flux should not be zero. So this equation guarantees the non-existence of the magnetic monopole. This equation. Okay. So we learned about the gradient. We just learned that. We learned from the one equation, this equation, gradient f dot v plus f divergence f divergence v, or the old version is divergence f v gradient f multiplied to v plus f divergence v. This is. I prefer this sometimes, correct? Because because when the system have more than 2 coordinate, 3 coordinate, and when the situation becomes very complicated, sometimes using the gradient will be confusing. So I use the word like divergence and gradient. That's very sensible, good to me. Okay, I told you this is a very important relation actually, and you use several times this equation. I just give you one example when this equation use it. You need to share your comments with me. So I wanted to know that which direction we need to go. That's important because if I have a lot of investigation and study about the potential theory from the mathematical point of the view. So if I want to share that, it was one semester just about the potential theory. Or 2 semesters I can just talk about the solution for potential theory. Maybe 2 semesters, believe me. Because it's a very huge topic. And you can study a lot of the different systems and solve the systems using the technique of vector, this potential theory. This is called the potential theory. So one application is that you have a type of the matter here, M, and this matter have a density, we call it rho. So when you increase the temperature of the system, if you fire here, you know that the thermal moves, the thermal flux, you will have a thermal flux. I mean, you will feel the temperature also somewhere else from the system. If you're standing here, you feel the temperature, yes? Why? Because it seems that something like the fluid comes to you, huh? Something like the fluids come. Exactly like the fluids which we know, like water, like everything. This is called a thermal flux. Huh? Thermal flux. Just using the concept of divergence, I want to find for you the equation which from this equation you can relate the density to the thermal flux. Density. So if I consider the temperature T, it's easy for you to understand that when the temperature is decreasing, it means that when the temperature is decreasing, it means that the flux is going exit the system actually. When the flux comes out from the system, so the temperature of the system is increasing. So I mean the change in the temperature with respect to times, that is the reason which we have a thermal flux, yes? Thermal flux. The first assumption. And the higher change in the T means the system colder, huh? Means the system colder. Because the temperature is leaving the system. So if the T changes very fast, I mean if the partial derivative of the T with respect to time decreased very much, so the system becomes colder and you will have a lot of flux they want to leave the system, yeah? That's a very easy idea. So if I consider the minus of the change in the temperature with respect to time, that's the rate of the flux which you get. If partial derivative of this decrease, so it means that the minus of one increase, yes? And you will have the more flux than the previous situation. So what's the flux? Flux is divergence of the something, huh? I already talked about that last whiteboard. So the only question is, what is this object? What should sit here? So here you need more physics actually, but you can know that at least you can understood that it should come some function of the density. So it depends to the density. So if the density changes, so the value of the flux will be changed also. So I mean it should be like that. And if the heat intensity be stronger, it means that the change in the temperature, not the time change. The speed of the change of the temperature in the speed is increasing. How I can write that? Gradient T gives you the idea about the change in the temperature in the coordinates. Huh? You have two types of the change in temperature. One is when you want to understand when the system becomes colder or hotter. So cold or hot means that when the temperature decreases or when the temperature is increasing. That's about time. You need that you understand that to see the system in coldness, you need to wait. So it's related to the time. So partial derivative with respect to time is the rate for the coldness or hotness of the system. And this is works like the velocity for you, like the fluid, you know. We needed to think about this phenomenon like the fluid. So how I can think about that? I can think about the change of temperature from this location to this location. Huh? And that is the gradient. So this equation, divergence rho gradient T, is the fundamental equations or the whole thermal convection phenomenon. In mechanical engineering, for example, a part of mechanical engineering is just heat control. They call it heat control. But they work only with this equation the whole life, just by these equations. But with different situations. Of course, if the geometry is very complicated, working with this equation very complicated. So they develop a new strategy to solve these equations. It's a finite element. So it's very common in mechanical engineering. I mean that for me as a theoretical